Today I'm going to talk a little bit about our project on Blue Waters, which involves a no-core shell model for advancing fundamental physics and astrophysics. And here's a giant list of people that are involved with this project, primarily professors, a whole line of grad students, some external computer science collaborators from the Czech Republic. There are also some undergrads and REU students involved, though they're not particularly working on Blue Waters, so they didn't get their names up here. And we also have a paid program project that I'll present on a little bit later that we've teamed up with people at Princeton for. So I think maybe I'm the only nuclear physics talk today, aside from the lattice QCD one that follows me. So I'm going to start really broad and then shrink into exactly what we do. So here's a phase diagram of QCD, everything from the core gluon plasma to hadron gases. And if you get all the way down here, you have condensed nuclear matter, i.e. nuclei. Of course, as you all probably know, nuclei are composed of protons and neutrons, which themselves are also composed of different kinds of quarks. And the nuclear interaction that holds together these nuclei is pretty complicated, right? So we've got the strong force that holds together each of these protons and neutrons, and then the residual strong force, that is the strong force that's left over, is what actually holds together nuclei. And because protons and neutrons themselves are composite particles, we also have 2-body, 3-body, and 4-body forces that also can arise. But even with all of these complications, all of these things that make our lives more difficult, there are a lot of potential benefits from really good nuclear theory. And so in particular, we can discover properties of nuclei at the edge of existence. So these are probably going to be astrophysical things that occur at really high temperatures or really extreme environments. We can also test fundamental understandings of nature. By that I mean primarily standard model tests. And more to that effect, astrophysics, as I mentioned, is a good place for us to apply these things, and in particular nucleosynthesis, both nucleosynthesis that occurs in X-ray bursts and in various R process things. And so this is the chart of the nuclei, just indicating where on it that nuclei important for X-ray bursts might occur, or Big Bang nucleosynthesis, and so forth. And then for our standard model tests, we have various neutrino detectors and a bunch of really interesting things that we can do there to see what we have. And so we'll go ahead and jump straight into how these nuclear models sort of go. So this is a flow chart here. So you'll want to start off with some sort of interaction. And there are people that devote their entire careers to developing good nuclear interactions. So primarily we just get them from other people. You'll plug that interaction into your model. And there are a bunch of different models as well that people devote their entire careers to. We use the no-core shell model primarily, though we've put a little twist on it. And from that model, you'll get wave functions and binding energies, equivalently eigenvectors and eigenvalues. And then from those wave functions, you can calculate all sorts of observables. And these are the things that people can actually measure in labs for you. These are going to be reaction rates that occur, again, in, say, astrophysical things, cross-sections for neutrino scattering, for instance, and nuclear densities. So a little bit more about the no-core shell model, in particular the ab initio no-core shell model. Its goal is to solve the non-relativistic Schrodinger equation for A particles, where A is just the number of particles you have in your nucleus. And that looks like this. H is your Hamiltonian. Psi is going to be your wave functions. E is the binding energies. And so the first step is to choose a really good basis and construct your model space. And for standard no-core shell model things, this is a basis of Slater determinants made out of single particle states. And then once you've got your basis constructed, you'll compute your Hamiltonian matrix. You'll find all the matrix elements for your Hamiltonian, where your Hamiltonian is whatever you've decided to put in it. These are going to be the interactions that you get from other people primarily. In particular, you'll want to have kinetic energy because particles move around. This is going to be a 2-body nuclear potential. You could include other ones there, 3-body, 4-body, so forth. And of course, the Coulomb potential, because protons still experience that. And then once you have all of your Hamiltonian matrix elements, you're going to find the lowest lying eigenvalues and eigenvectors, typically by the Langtius algorithm, but there are other choices. And these lowest lying eigenvalues and eigenvectors are going to correspond to, again, binding energies and the wave functions for these nuclei. Okay. So the standard approach does really well for light nuclei, and it has for a long time. However, there are some challenges as you go to heavier and heavier things. And so this top graph displays that. We've got dimensions. This is the dimension of the matrix that you're constructing, of the Hamiltonian, as a function of Nmax, where Nmax is just a truncation parameter that controls how fast your model space grows. And so you can see that for these heavier ones, you're barely getting past Nmax 2, which is probably not going to yield very well converged results that you would want to report on. This red line represents one potential guess as to what the best supercomputer today could run. And so this is around 10 to the 10, so 100 billion by 100 billion matrix would sort of be the stopping point for traditional no-core shell model things. And so this bottom graph is again just emphasizing that it's limited to the light nuclei. So if we considered this is the chart of the nucleides, and this darker blue one is indicating what some other models can do. The no-core shell model did well in extending the reach of ab initio theory, but again, it's sort of preventing us from getting up here where lots of interesting, rich nuclear physics is happening. And so we wanted to try to get away, or find a way around that sort of computational stopping point right there. And so we've decided to try and use a different basis from what standard NCSMs use. And so we constructed our basis from physically intuitive things. So these blue numbers, or these blue letters rather, are all quantum numbers that you can use to label our many-body basis states. So N, don't worry a whole lot about that, but that corresponds to Nmax that I mentioned earlier, right? That sort of controls your truncation. Protons and neutrons still have spin, so you'll want to label your basis states with spin. And this is the really interesting part. If we label it with these SU3 quantum numbers, lambda and mu, they have a really physically intuitive interpretation. So 0, 0 corresponds to a perfectly spherical shape. Lambda 0 to a prolate shape, 0 mu to an oblate shape, and some other combination of lambda and mu to some triaxial deformation. And additionally, this other quantum number L that corresponds to SO3 is going to have rotations. So each of these shapes could rotate according to this quantum number. And so our basis, as constructed like this, is really finely tuned to describe highly deformed and rotating objects, which nuclei definitely fall into that category.
Are lambda and mu integers?
Yes, they are integer quantities, yes. So if we take all of this that I reported down here and implement it into a code with some MPI and OpenMP, it turns out that calculating the matrix elements themselves take up 95% of your computational time, and finding the wave functions and the eigenvalues takes up a mere 3%. So this is really the part that we have to focus on, calculating the matrix elements. But luckily, it's highly parallelizable because most of these matrix elements are completely independent of each other, so we can easily just put them on however many nodes we want and let them run. But of course, we have to make sure we properly load balance, but we can handle that pretty well. This would be if we just had one matrix. You can sort of see that this matrix is somewhat sparse. So again, you have to worry about making sure you load balance, but we handled that on Blue Waters. And the algorithms we've developed also scale really well, both in terms of OpenMP threads and in terms of MPI processes. And so everything I've told you so far wouldn't really convince you that this approach is better, right? I've just said we've picked a different basis and we're going to use it because we like it better. But it turns out this basis has another great property that we'll talk about now. And so this is a representation of the model space for lithium-6 for Nmax 12. And this bottom axis is different lambda mu configurations, so different shapes that we've included in this basis. And then the horizontal, or the vertical axis rather, is the spins, the allowed spins. And each of these yellow dots corresponds to some subspace of states that all fit in there. And this lithium-6 calculation, if we were to run it all together, is about 4 million. So 4 million by 4 million matrix. And it turns out, if you include literally all of these states, and you run this calculation, that the interaction that you have sort of tells you that lithium-6 doesn't care a whole lot about most of those. So let's see. The horizontal here corresponds to these lambda mu's again. And you can see that there's a strong piling up on the right side here. And so the right side corresponds to the highest deformation. And these colors that you can sort of see correspond to the spins. And red is the lowest spin. So for this lithium-6 wave function that we decomposed into its SU3 states, over 60% of that wave function comes from just this one lambda mu state. And that trend continues upwards along the right side here. And these left side states, there's hardly anything in there. You'll notice that the axes on the right are on the left rather decreasing as you go up. And any states that don't appear here have no contribution whatsoever. So there's not a whole lot of reason to include them in the calculation. Of course, now you might say, but wait, is this just a thing that occurs for this just one state in lithium-6, or is this something that you can apply to everything else? And it turns out that it occurs for other states in lithium-6. And so this is the 1+ state that I just showed you. This is the 3+, 2+, 1, another 1+ state. And so if you include literally all of the model space and run the calculation, the resulting wave function every time comes out to prefer these low spin, which are on the right now, and these high deformation states, which are all these yellow dots. And this continues to occur for other nuclei as well, although I don't have other graphs to show you, but it does. We've done many calculations indicating that. And so we can use this property then to study heavier nuclei that are beyond the reach of other models. And so here's some really good results for neon-20 that I'm going to report, or that we've previously reported. And so if we apply this approach to neon-20, this is for a good number of different states in the ground state rotational band, we can see that the binding energies, or rather the excitation spectrum, agrees very well with experiment. So these are the experimental values, and these are the results that we get from the SA and CSM. And they're almost perfect, right where they line up. The binding energy for the lowest, for the 0+ state, is converging as you increase Nmax. So the higher lines are going to be less Nmax. The lower lines are going to be more Nmax. You can see they're sort of starting to converge, as we would hope. And you can also calculate density profiles and find out what these nuclei sort of look like on their own. And again, if you were to use the whole space here, you would have had something on the order of 4 times 10 to the 12, which I think is a trillion, 4 trillion. So 4 trillion by 4 trillion matrix, which is a rather large matrix, and you would have a lot of difficulty storing all of those matrix elements. But with our approach, the symmetry-adapted approach, we can cut that down by 5 orders of magnitude, so just 10 million by 10 million. And so that does it for the PRAC bit. Now I'm going to talk a little bit about our paid program. And so if you'll remember back to that first slide where I had that flow chart, we've been focusing mainly on the middle part, on the model part. But I want to talk a little bit more about the densities now, because we have a paid program that focuses on the densities. And in particular, we wanted to improve the computation of those density matrices by using GPUs or Intel mix, either one or both, in fact, because henceforth we haven't been able to utilize the GPU nodes that Blue Waters has to offer. We've just been using just the XE6 nodes. And so calculating these density matrices involves a vector matrix vector multiplication. And these vectors are the wave functions that you've already calculated from the previous step. But this matrix has to be calculated for the first time, every time. And once we started this project and really started to focus in on how to improve this computation, we realized that this matrix that you have to calculate, which is both large and sparse, is made up of a very small set of small, dense submatrices. So that's sort of what this is attempting to emphasize right there. And so it was decided that maybe if we only compute these submatrices and then do a vector submatrix vector multiplication on the fly, we can outsource that to a GPU or to a MIC. And so we went around starting to change up our algorithm, collaborating with our Princeton people to try and make that happen. And it turns out, once we've got that implemented serially, that the serial implementation is 4 orders of magnitude faster than the previous attempt, right? So 10,000 times faster. I don't know how often that happens in your research, but that was dumbfounding when that happened for us. So that's the serial implementation. It's 10,000 times faster than how we were doing it before we started collaborating with the paid program. And we've already got an OpenMP implementation done for the mix, and it scales just as well as our old one. So this green one is our old version, and this red one is the new version. They both scale very, very well, but again, keep in mind, even though they scale about the same, this new version runs so much faster. So it scales really well, and the GPU implementation is under heavy development, and we look forward to employing that on Blue Waters whenever we get it done. And so I'll summarize a little bit. Collective modes arise naturally from first principles, right? So that's the shapes occur when you do these calculations. There's a dominance of certain shapes that occur, and that's coming straight from just the first principles interactions that we're using, the realistic interactions. The physically relevant basis provides a useful truncation scheme. So this is, again, certain shapes dominate, so let's just include those because they're physically relevant, whereas these other ones don't seem to be having much effect on our wave functions, on our results. Other applications of this to higher mass nuclei are underway. So titanium was mentioned in my abstract. We're working on that. We have other neon isotopes that are important for other nucleosynthesis things that we're also looking at. And of course, our collaboration with the PAID has greatly accelerated our ability to discover, accelerated our ability to provide science, and we really look forward to continuing that in the future, both on Blue Waters and other systems. So this is, again, that same toolbox, that same graph from before. You can see that the SAS NCSM has extended the reach a little bit further now as well. And then lastly, I'll acknowledge some funding and supports, in particular support coming from both the PRAC and the PAID program, previous funding from NSF and DOE, current funding from SURA and LSU, computational acknowledgements to both Blue Waters and LSU. And I'd be remiss if I didn't say that LSU 3 shell, the code that we use to run NCSM, is publicly available on SourceForge. It's free to download, and you're free to do anything you want with it. The more recent PAID codes that we're using, the OpenMP version for the density matrices, those are not yet available on here, but they will be eventually once they're stable. All right, thank you.